Welcome to the Leading with Lidar webinar series. Today's topic is on the practical uses of scanning Lidar for wind energy applications. My name is Greg Shambo, and I'm broadcasting in the Boston, Massachusetts area today. I'm joined by Andrea Renette, who is in our Paris office and will be presenting from there. I head up Leosphere, a Vaisala company's North American renewable energy group, and for the past 10 years, I've been working with companies like yours on using remote sensing to solve problems and for various applications throughout the wind development and operations cycle. Andrea is the Leosphere WindCube scanning LiDAR product manager. She's an industry expert. She has 2 master's degrees. One is in renewable energy engineering, and the second is in applied physics. Andrea, thank you for joining us today. Today, the 3 things that we're going to try to talk about and hopefully you walk away and learn from is, number 1, how does a scanning LiDAR work, including the functional overview of a scanning LiDAR and its systems. Number 2, an overview of the most commonly used applications that companies like yours are using scanning LiDAR for. And number 3, I'm very excited to share 4 real-world case studies that prove adding scanning LiDAR to a wind energy project, whether it's development or operations, can increase value. We also have a bonus slide to talk about some future and emerging scanning LiDAR technologies that other people are using today. So you should see a poll that just showed up on your interface. And if you don't mind selecting which of these areas is your primary focus, onshore, offshore, development, operations, turbine manufacturing, consulting, or research, or other, we'll share the results with you in just a few minutes. This helps us design our future series and our future webinars so that we can ensure that we're targeting the right audience groups. So we appreciate if you could fill that out. So this webinar is specifically designed to leave plenty of time for a question and answer section. We're going to pause after each case study and answer any questions that have come through. And the way that you can submit your questions is at the bottom of your screen in your interface, you'll see that purple Q&A button. And if you click that, a window should appear in the upper left where you can submit your questions. These can be submitted anytime. We're already getting lots of questions that are coming in. And also, we will, if we don't get to those questions throughout the webinar, we will make sure that we follow up and send them to you. If you're having any technical issues, there's a question mark at the bottom of the screen that you can click on, and this will bring up some common issues with some suggestions on how to solve them. And also, we're going to play 3 short video clips. And when these play throughout the presentation, your media player will pop up and probably block your presentation view. So the videos are 10 to 15 seconds each. You can simply minimize your screen if you don't want to see them, or to move it out of the way. And lastly, there's a resource section on the left-hand side that you can see here on your slide where we have put in some files for you to look at, and those 3 videos are also there. If you're having audio trouble, you can dial in through the phone number that was provided. And a lot of us are working from home. We may not have the bandwidth that we need, or there's actually lots of people on this webinar. If you feel as though that the slides are lagging and with the audio, you can simply press F5 in your browser, and that should refresh everything and bring it back in line. And we will be sending out the recording of this webinar as an email follow-up. Okay, so now we're looking at our poll questions here. So we've got almost half of the group that's interested in onshore, good percentage for the offshore, 44.8% for development, and have a good representation on the consulting and research slide. Before we get into the actual case studies here, I want to first send out a special thank you to the companies and people and agencies that participated in these case studies. They're extremely useful and beneficial for our industry. And last but not least, my warmest thank you for everyone that is joining us today. The 400 plus people who signed up for this webinar are from 56 different countries. And it just represents our effort and drive to try to keep things normal in this new normal. And I really appreciate people taking the time to join us. So with that, I'd like to pass it off to Andrea.
Yes, thank you, Greg, and thank you everyone for joining us. So as mentioned, I will do a quick presentation on scanning Lidar technology and a quick overview on the different applications in wind energy. So to start with, I will quickly explain how the scanning Lidar works. So all our system use pulse heterodyne Doppler Lidar principle, which means that our system are sending several latest pulses into the atmosphere, and these pulses are reflected by the particles moving at a specific wind speed, and this light is backscattered with a shift in frequency, and this shift allows us to estimate the radial wind speed. And what is really unique about the scanning Lidar is that we can get a full 3D mapping of a specific area of a few kilometers squared. So our system have several scanning patterns. So we have here the PPI, the plant position indicator. You should be able to see a quick video on the media player that is showing how the scan is visualized in the software. So it's a scan with a fixed elevation and moving azimuth until 360 degrees. And on the software, we can see the radial wind speed, so the wind speed along the line of sight. So then we have the RHI, the range height indicator, and this scan is with a fixed azimuth and a changing elevation from minus 90 degrees to 199. And in the video, you can see the same thing as the PPI, so you can visualize the radial wind speed in real time on our software. And then we have the DBS, the Doppler beam swinging. This is the profiling mode, which is the same type of scan as the LiDAR profiler. This scanning pattern is using 5 laser beams, so 4 are cardinal points and 1 in vertical. And this allows the user to reconstruct the wind speed at several heights, so to get the horizontal and vertical wind speed as well as wind direction. So we have 3 types of scanning LiDAR that go from 3 kilometers to 10 kilometers, and this depends on atmospheric conditions and the LiDAR configuration. It's an all-weather industrial design, meaning that it can be deployed onshore and offshore in hot and cold weather. It's a cost-effective solution compared to conventional sensing instruments. It provides NetCDF files, which is a robust auto-documented format that allows the user to have all information into one single file. The system can be monitored, configured, and programmed through a very user-friendly software or API request, and the data can be exported as well with through an HTTP server. The system can be provided with a wind reconstruction tool that has been validated by international third parties, which gives the user horizontal wind speed and direction from radial wind speed. And we benefit from a full service range going from on-site maintenance to project support. So on project support, typically on a wind farm project, the developer will have several questions on how to validate the mesoscale data for $1 billion offshore project, or how to assess the wake loss, or how to calibrate a wave model. And for this, they will need to do a design of the wind measurement campaign, so what type of data is needed in what specific site, what type of instrument is needed, and how do they operate and monitor the system, and how do they process the data. So for each one of these steps, Leosphere or expert partners can go with the client through each one of these. So for the campaign design, we can contribute on the seating of the WindCubes, how to choose the ideal location, how to configure the WindCube on the type of scenario and the type of scan. And we can also provide project management, assist the client on how to install the system, what is the ideal setup, what type of power supply needs to be used, as well as training the user on how to operate the system, monitor, and also how to configure the system or the network. And on the data processing, we benefit from a suite of software to process the data, and we can also scientific support, so our Leosphere scientific team that can help the client on the data processing and the data analysis, as well as giving data training.
Thank you, Andrea. Now we're going to jump right into the wind energy applications and the use case. So we're going to provide a summary of 4 use cases. The first one is around how to reduce spatial uncertainty when you're performing wind resource assessment. And in our case, it's going to be for an offshore wind project. Our second case is around power curve testing and how you can use scanning LiDAR to help with power curve, again, for another offshore project when there isn't a met mast available. Our third one will be around wake modeling and uncertainty and how to calibrate our wake models with scanning LiDAR measurements. And the last one is going to be on short-term forecasting and how to use scanning LiDAR and some techniques to help with short-term forecast in areas that require high market reaction. And again, if you could, please, while you're listening to these overviews, if you could put your questions into the Q&A section, that would make this a lot more valuable for everybody and more interactive. We're going to pause after each case study for a few minutes and review those. And again, we will have more Q&A section at the end of the webinar. So Andrea, please kick us off with the first one. Thank you.
Yes, thank you. So for the first case, we're looking at a wind resource assessment offshore from the shore campaign, and more precisely on how to reduce the uncertainty of offshore models. So the developers can face several challenges on this type of application. So first of all, that the spatial uncertainty due to the models, the wind offshore models can be quite high and can reach up to 2.5%. And any percentage of uncertainty for offshore projects can be very costly for projects that are already billion-dollar projects. So in this case, one of the solutions will be to calibrate mesoscale data with the scanning LiDAR data over a few kilometer squares. So we're going to have a look here on a campaign done by Engie, a French operator, where they did several measurements at multiple distance and heights. And a LiDAR vertical profiler was also installed to correlate the measurements from the offshore to onshore condition and to assess the land-sea interaction effect. So in this case, they install, more precisely on the scanning LiDAR, they install a 400S, so our system that can typically reach up to 10 kilometers. It was a campaign of 6 weeks in the coast of southern France, and they were looking at to measure up to 9 kilometers from the coast. So here we have the scanning LiDAR data from the wind direction in blue compared with the ones from the mesoscale data, so that we can see that the wind direction measure from both data sets are in line. And in here we have the comparison on wind speed. So on the vertical axis, we have the percentage of correlation between the two data sets. And on the horizontal axis, we have the distance from the shore for three measurement points, so at 0, 5, and 9 kilometers. So we can see here that the further away we are from the coast, the closer the mesoscale data is to the scanning LiDAR data. So the relative error is higher near the shore, since the rugosity and terrain effects are more important. So in this case, the results that are published in a poster for the AWEA conference they shown that the scanning LiDAR data was assimilated to the offshore wind model to decrease the uncertainties and improve the overall assessment of production for the future wind farm. And a significant error was found in the mesoscale data near the coast, and correction factors were identified for this. And they noticed that the spatial uncertainty can be decreased significantly with scanning LiDAR type of instruments.
Okay. So we have a couple questions coming in. And again, we're going to send out these case studies for you to read directly after this webinar. So the first question here is, can I use a scanning LiDAR to reduce spatial uncertainty onshore, because the example was for offshore, and if so, how would you go about designing a good measurement campaign?
Yes, so most of the applications that we're looking here are equivalent onshore and offshore. So the same principle can be done for onshore campaigns. But they have seen more interest in the offshore for the time being, since there might be costly offshore metmasts to be installed. So the fact of using a scanning LiDAR from the coast allows the user to have a full map of the area. But this can be done as well on onshore.
Okay, great. So it can be used for both onshore and offshore. We have another question here. Does it require a on-site calibration?
Yes, or well, it would depend on the user, but most of the time they rather calibrate the system with IAC compliant metmasts. For example, we do that with external partners such as DNVGL, that they validate our scanning LiDAR at the test site with one of the metmasts, and this can be done for this type of campaign. I mean, before starting the campaign.
Okay. Let's take one more before we move on to the next case study here. Someone wants to know if they can install the scanning LiDAR on a fixed platform, offshore fixed platform instead of the coastline, and what are the drawbacks or benefits of doing it one way or the other?
Yes, the scanning WindCube is designed to resist tough environments. Its components are integrated in an ultra-resistant one-piece fiberglass casing protected by gel coat finishing. It is waterproof with an IP65 rating and resistant to salty environment, so it can be installed whether on a fixed platform or near the coast. The drawbacks, I will say, is that installing the system on a fixed platform will require to have a fixed platform. So in the case of the user does not have anything installed offshore, the ideal installation setup will be near the coast.
Okay. All right, I lied. We're going to do one more because it's a follow-up from a previous question. Can you explain the difference between calibration and or validation? There's some confusion to that with the scanning LiDAR.
Yeah, that's a kind of a complex question. Well, the system can be validated. For example, we do the validation at factory by comparing the scanning LiDAR with golden LiDAR, but the certification will have to be done following IAC requirements from the standards. The only thing is that the scanning LiDAR does not have an IAC standard to follow, so the certificators, they follow their best practice criteria.
Okay. All right, let's move on to the next one.
Okay, so for the next use case, we're looking at power curve measurement. So the operators can face several challenges for this. First of all, because of doing power performance verification, offshore can be very costly and time-consuming if there is not an offshore metmast. and installing a NASA Lidar might not be an option due to warranty reasons or others. The solution here will be to use scanning Lidar on the transition piece to do hub height wind measurements. So in here, we're looking at a campaign done by SSE, so an English operator with DTU, the Technical University of Denmark, and they did a full report where they published all this, the results of this campaign. So in here, they installed WindCube 100S with a WindCube nacelle. They did a 3-month campaign at the Greater Gobar offshore wind farm in the UK. And as I mentioned, they installed the scanning LiDAR on the transition piece, and they pointed at the top anemometer, and they compared the data here from the scanning LiDAR and the landmass, as well as from the nacelle LiDAR. So in this case, we have here the power curve from all the instruments. So here on the vertical axis, the power, and on the horizontal axis, the wind speed. So we can see that the mean average power curve for all the instruments correlate very well. And on the result of this campaign is that although the power curve uncertainties measurement were challenging due to several parameters, the difference between the LiDAR and the power curve were relatively small. And through this campaign, they managed to do a power curve verification using scanning LiDAR and a possible identification of on the performances.
All right. Well, we're getting a lot of questions on this one as well. So one question here is, why should I install a scanning LiDAR instead of a nacelle-mounted LiDAR for an application like this?
Yeah, a scanning LiDAR can be a good alternative when a nacelle LiDAR cannot be installed due to warranty reasons, for example. And also it can be interesting for the user when they want to look at the power verification of several turbines at the same time.
Okay. Someone wants to know, what are the benefits of using both the scanning LiDAR and a nacelle-mounted LiDAR for power curve testing versus just one or the other?
Yeah, well, the main benefit will be that we have a redundancy of data because we can compare the scanning data with the nacelle-mounted. So this is always an interesting point to make sure that the measurements that we're doing with one instrument is in line with other type of instruments. So it's mostly the redundancy on the data.
Okay. How long does it take to gather enough information from the scanning LiDAR and the nacelle-mounted LiDAR to perform a power curve test? Well,
that would depend on the, well, in this case, we're doing tests for several weeks, but I mean, the scanning LiDAR, you can program so that the scan itself could last a few seconds or a few minutes. So you can already compare the data in a one-day basis if it is needed. And most of the time they use average data, so it might be 10 minutes average data, and that can be possible as well with both instruments.
Okay. Someone wants to know if they can put the scanning LiDAR on top of the nacelle of a wind turbine.
Yeah. So the scanning LiDAR is the scanning WindCube is a light and compact system. Its weight is less than 250 kilos, but the system can have a degradation on the measurement accuracy or the critical components lifetime due to vibration of the turbine, and this will be much less if it is installed in the transition piece. So that is why our offshore clients usually install the scanning WindCube on a transition piece or on a fixed platform.
Okay. All right, we'll do one more here. This is a good one. So someone, their question basically is asking that there's choices for LiDAR, whether it's on the ground, vertical, like a WindCube vertical profiler. We have a scanning LiDAR, and then the nacelle-mounted LiDAR, like a Wind Iris. How do you choose which one would be the best, or what combination would be the best for power curve measurement?
Well, I guess it will depend also on what is the purpose of the client. If he wants to look at just the power curve for just one turbine, a nacelle mounted and a ground-based profiler might be enough. But if the user wants to look at several turbines at the same time, it might be more interesting to have a scanning LiDAR.
Okay. Okay, great. Well, let's move on to the LiDAR wake measurements.
Yes, so for LiDAR wake measurements, the main challenge is that a significant part of the annual energy production uncertainty comes from the uncertainty of the wake models. And this can be more challenging offshore since wind turbines' wakes will decay more slowly than onshore due to lower turbulence levels, which will require larger separation distance between the turbines. So in this case, the user wants to have a better characterization of the velocity deficit, the wake length, and the wake centerline deviation. So the solution here is to use a high-resolution measurement from the scanning LiDAR and use the measurement from this system to calibrate the wake model. So we're looking at a campaign done by several players. We have the University of Bergen, Stavanger, and Notre Dame, and CMR, which did a publication on this campaign as well. And they installed WindCube 100S at the Alpha Ventus to look at the Alpha Ventus wind farm. So the system was installed in the Final One research platform, and they did a campaign for 4 months in Germany. So in this case here, we're looking at the analysis of the velocity deficit. So we have here on the vertical axis the percentage of velocity deficit, and on the horizontal axis the distance from the turbine, so in rotor diameters. And we see here that there are 2 trends where there was noted in this campaign. So the first one, we see an increase on the velocity deficit in the near wake region up to 2 rotor diameters. And then we see an exponential decay of the velocity deficit till it reaches the free stream velocity. So in this campaign, they propose a regression fit and other existing models to see how it behaves with the observational data. So in here, we can see as well the wind turbine wake. So we have the LiDAR wind speed measurement. We have the LiDAR position in the top left. And we see here in blue the decay on the wind velocity. So through this campaign, they noticed that there was near wake and far wake behavior, and they proposed models for each region. And they noticed that the scanning LiDARs helped to bridge this gap between models and observation. And another thing that they saw was that the wake's length during nighttime could be between 4 and 11% greater than the one from the daytime.
Okay. Okay, first question. What type of resolution is used for wake measurement applications?
Yeah, the characterization of wakes require a high-resolution measurement. So in this case, they use WindCube 100S. So it's a system that has 4 configurable resolution at 25, 50, 75, and 100 meters. And so in this case, they were using 25 meters, so it was the smallest resolution to have a better quality measurement and characterization of the wake.
Okay, and here's another data question about how long does it take to capture enough data for a good wake study?
This also would depend on the purpose of the campaign. So in this case, they were looking in a day frame. So they were looking how the wake behaves during the daytime and the nighttime through several days up to several weeks to compare the behavior. And it will also depend on eventual constraints from the wind turbine. If the wind turbine is working only on a percentage of the time of a specific week, it will depend also on that.
Okay. We have a couple of questions around complex terrain. Maybe this is a good point to talk about that, whether it's in relation to a wake study or using the scanning LiDAR in general in a complex area.
Yeah, that's actually one of the applications that is also having more interest since there's an increasing size of the wind farms, and there are more wind farms installed in complex terrain. the fact of doing a full mapping of the area is a big benefit. So we have seen also this interesting in understanding better the wind flow in complex terrain, and the scanning LiDAR can be really useful for that. And they can also do the wake analysis in this type of area.
Okay. There's also been a few questions asking if these reports are going to be shared. Yes, we will follow up after the webinar with a link in an email, and you can download all of these. Let's move to the short-term forecasting one.
Yeah. So for short-term forecasting, we have seen as well an increasing interest in this application. As the share of intermittent renewable energy into the grid grows, the requirement for the grid stability become more important. So, the operators have to have a better forecast, more accurate forecast on the electricity production, and this electricity market requires high reactivity. So the forecasts are normally based on statistical models or spatial correlation models, but these methods can show some errors. So here the solution is to use scanning WindCube to provide measurement up to 10 kilometers to forecast new coastal wind conditions with a lead time of 5 minutes. So this was a campaign done by University of Oldenburg and Forwind and DTU as well. In this case, they installed 3 WindCube scanning 200S during 3 months for a campaign in the western coast of Denmark. So in here, they install the 3 systems in new coastal area. The one in the middle was doing several PPI, so several sector scan at different elevations, and the 2 others were pointing at the same height in order to match positions of the 3 levels with the other LiDAR in the center. So in here, they were looking at the wind speed forecast measurement out to 5 to 6 kilometers from the shore. And they were also doing modeling on coastal effects with the dual setups from the sides by having the 10 minutes average data up to 3 kilometers. So we have here the wind speed data in a specific time frame, and here we have the LiDAR data in black compared to several objection models. And these models were taking in a different level into account the site-specific conditions, whether it is because of roughness, orography, or height. And this model will also compare to commonly used statistical models, and they noticed there was an improvement up to 4 and 28% in stable conditions by using these objection models with the LiDAR data instead of using the statistical model. So in this campaign, the scanning LiDArs, they show they can provide information on site-specific effects and give a more accurate forecast since it has less uncertainties, especially during ramp events where there is a large variation in wind speed in a short time period.
Okay, first question. What's the maximum range someone can expect with using the scanning LiDAR?
The maximum operational range will depend on the LiDAR parameters and also on the atmospheric conditions. So that is also why Leosphere developed a simulator to estimate the maximum operational range of the WindCube for a specific project. And this takes into account the WindCube architecture and configuration and the local atmospheric condition of historical data. And these principles used in the simulator are based on the ISO and WMO standards. And this is how we can get a clear idea of what to expect for a specific site. And the simulation can be provided on open request for any type of project.
And in this example with the short-term forecasting, the question is, why should I use a scanning LiDAR instead of a WindCube vertical profiler or even a MET-MAS?
Well, there is a significant benefit from the scanning LiDAR is that it can provide a full 3D mapping for several kilometers, and this is an important asset for the increasing size of wind farms. So being able to estimate the wind speed several kilometers ahead allows the user to forecast the wind farm production for several minutes more precisely than it will with a punctual measurement from a MEDMAS or a vertical profiler, that this might require to do some extrapolation or assumptions.
Okay. I think our next slide here, all right, are the conclusions.
Yeah, so we have seen that the scanning LiDAR is used in different type of application, which makes it a very flexible and cost-effective tool that can be used from development to operational type of campaigns. So with the increasing interest in scanning LiDARs in wind energy, also comes an increasing number of possible applications. So as we were mentioning, there is also an interest in onshore wind flow characterization in complex terrain, since this requires a more accurate wind flow study. And here we can see the wind flow, the wake that is produced by this wind turbine on the top of a hill, and this can be analyzed through a mapping of one or several scanning LiDARs. And another topic of interest in currently is the blockage effect studies. So this is a topic that is having an increasing interest. This was not usually taken into account until now, even though the turbine interaction losses, so the blockage effect, can have an impact on the overall wind farm production. And this is where a full 3D mapping of a scanning LiDAR can be of great benefit to really understand the wind farm layout, how the wind flow is reacting. So here we have some customer success quotations from some of our clients that are also stating on the fact that scanning LiDAR is a tool that can help reducing the risk on spatial variation due to models, reduce the cost of energy, mostly in offshore wind. It can be a great tool to support research and optimize wind farm, and also is a tool with a high efficient and time cost effective alternative to conventional MEDMAS.
Okay, I think that brings us to our second and final poll that we want to ask the audience here. What future Leading with LiDAR webinar subject you would like us to address? And this also brings us to our question and answer section. So while you're filling that out, I will ask a few more questions, Andrea. We're actually, it's just overwhelming. We have over 100 questions in so far, so we definitely won't have enough time to answer everyone's question. I'm trying to view them as they're coming in and maybe group them into a more generic question that will benefit the audience, but we will make sure that we get back to the individuals and everyone on the webinar directly regarding the questions that have been asked. So I have a question here that talks about, there's many questions around service and maintenance. Can somebody be trained to install it themselves? Do they need a special training to understand and use the data? So Andrea, maybe the question is around, can this be user installable? And if so, what level of training is there available to make someone self-sufficient using this type of device?
Yes, for the scanning LiDAR, we have several levels of training. So we have a first level that we call L1, which is a really basic training to let the user understand how to operate the system, how does the hardware works and how the software works. And this is done with every system that is sold. A field engineer will go to this deployment site and will train the operators on how do they use the system, how do they install it, how do they configure the network, and how to use the software and the data from the LiDAR, and how to do some basic troubleshooting. Then we have two other training levels, the L2 or L3, and this is more advanced so that the operator is autonomous enough so that he can do maintenance by himself, or different levels of maintenance by himself.
Okay. So we have another grouping of questions around that our 4 examples were for offshore, and that was just by coincidence. These were the ones that we selected to portray what the scanning LiDAR system can do. So the question is, can they use it? Can someone use scanning LiDAR for onshore applications? What are the onshore applications, and is it still cost effective to do so?
Yes, as you mentioned, Greg, this was pure coincidence that we did only offshore use case. But of course, each one of these applications can be done onshore. And as we mentioned, with the increasing size of wind farms, tools such as scanning LiDAR might be really helpful in order to do a kilometer square mapping on the whole wind farm onshore. So this is also has some value onshore applications.
Yeah, and the more using multiple measurement devices, both for onshore and offshore, I think can be valuable. And certainly a scanning LiDAR can be used, like you said, for the site assessment, whether it's greenfield or for prospecting. It can be used for spatial uncertainty reduction. So there's lots of different applications. You can use it either on its own or complement some other measurement device. There's a bunch of questions around power. What is the power consumption? Is this something that you could connect to a remote power supply, or does it have to be plugged directly into line power?
Actually, the power requirements for the scanning LiDAR are up to 1,600 watts, this including the heaters and the coolers of the system.
Okay, so it sounds like it's something that would typically be plugged in to a source of line-in power unless there was a pretty significant remote standalone power supply. People are asking to describe, is it something that 2 people can lift up and move easily? What are the dimensions and weight of the device?
The system is a bit more than 1 meter cube, and the weight is 230 kilos. So for one person, it's a bit complicated, so we usually recommend to manipulate the system between 2 persons. So for the installation, we put some wheels to transport the system, and then we fix the feet so that it's directly installed on the site. But we recommend at least 2 people to handle this type of system.
Okay. So there's another series of questions around how long does it typically take to install, and do people normally install it once and leave it in that on a wind farm, for example, for years and years, or is it something that gets installed and then gets packed up and moved on to another application or another use case?
Well, the system is pretty easy to install. It can be done in less than 1 day, and typically our trainings that goes with the system last around 2 days, so the time that the field engineer will train the user on the hardware and the software and installing the system. And then we have several clients who have done all type of applications. So it depends on the purpose of the client. We have clients who wants to do one application during several years, and then we have clients who want to do just analysis of some wind turbine weight, and then they want to look at short-term forecasting. So they might change the position of the LiDAR, even though it is still around the same wind farm. So it will depend also on the application and the type of client. Okay.
Very similar to some of the other ground-based remote sensors, like the vertical profiler. We have a question around the laser source. What type of laser source is it, and are there any advantages to that laser source?
Well, our laser source is a pulsed laser at 1.5 micron, and it is a class 1M laser, so it's completely eye safe and it's according to IAC standards.
Okay. We have another series here around data recovery and different heights. So someone's asking, first, is it true, are there different levels of data recovery at different heights, and if so, what would be the reason for that?
Sorry, I didn't understand very well. How to recover data at several heights? Is that the question?
Yeah, we have, why are there different levels of data recovery rates for different heights or different positions of those scanning LiDAR?
Well, once again, it will depend on the type of scan. So, for example, if you're doing several PPIs, one PPI can be done in a few seconds if it's a small sector scan. And after each scan, the system will create a new file. So if it is, for example, connected to a FTP server or there is an API request to export automatically the data, after every scan that is played, there will be a file created. So it could be in a matter of seconds.
Okay. So maybe we'll take one more grouping of questions here, and it looks like it's around how is the data presented to the end user? So if you install this, the scanning LiDAR, how can you get the data and use that?
Well, it depends again on the application, but the raw data from the WindCube is radial wind speed, so the wind speed along the line of sight. And for most applications in wind energy, what they need is horizontal wind speed. So that is why we can provide with the system a wind reconstruction tool that will estimate the horizontal wind speed and wind direction from the radial wind speed. So this is the output data that is of interest for most wind energy players.
Okay. And does the scanning LiDAR transmit the data through directly to the end user, or do you have to go to the machine and pull the data? How do you actually physically get the data?
Well, you can get the data either directly to an FTP server that you can configure directly on the software, or you can export it manually from the graphical user interface, or you can get it from API request. And in this case, you will get NetJS files or in JSON stream, the data. So that will be the end data, the raw data from the LiDAR that the user will get.
Okay, perfect. Well, thanks for being in the hot seat there, Andrea. There's a lot of good questions. Again, there's just so many of them coming in here. We will make a commitment to get all these answered. I really appreciate everyone's response and sending those in. I think it makes it more valuable for others listening. If you have a question in your mind, somebody else probably has the same one. So appreciate the sharing of knowledge. You should be seeing the poll results now for the interest. It looks like we have wind resource assessment as a leader for a topic that people are interested in, with general laser technologies, how it works, laser types in a close second. We'll take that into consideration as we design our next LiDAR series. And with that uses up about the whole hour. We want to say thank you to everyone. Andrea, thank you for answering those questions and giving us an overview of those cases. I want to thank the companies and people that were involved in the actual use cases that we talked about here. Again, we'll be sending those out to everyone in the group. And thanks to all the participants that are online and held in here all the way to the end. We appreciate your support. Thanks for doing what you're doing. And we will be in touch soon. Have a great day, everyone. If you have any questions, you can contact me. My information there is on the title slide, or you can come to us through the web interface as well. with that, we'll conclude this webinar series. Thank you. Have a great day.